My talk today is about mechanism of uranium-234 enrichment in waters of carbonate terrains under supervision of Professor Vital Boukman, Professor Mordechai Stein, and Professor Boaz Lazar. First of all, I will show you the map of Dead Sea watershed. In this map, I will show the activity ratio of uranium-234-238 in the main water bodies in the Dead Sea watershed. For example, in the activity ratio uranium-234-238 in the Sea of Jalil is 1.73, but the activity ratio in the Dead Sea is 1.44. This value is significantly higher than the value of normal saline water. For example, in the Mediterranean Sea, the activity ratio is 1.14. So our aim is to know what the mechanism or factor controls uranium enrichment in water bodies. And the questions here, what causing the enrichment of uranium-234, 238 in the Dead Sea and the Sea of Jalil. Here I show you that the hydrological cross-section, and I show you that we can use uranium activity ratio as a hydrological and geochemical tracer. For example, in unweathered rock, older rock than 1 million years, the activity ratio is 1. But the activity ratio is different in surface water, and the value ranges from 1 to 2. But in percolation water, the activity ratio is 1 to 3. And the activity ratio in the ocean, 1.14. So the values of activity ratio changes according to the interaction, water-rock interaction. And so we can use uranium activity ratio as a hydrological and geochemical tracer. To define what the meaning of the activity ratio, I will start to speak about uranium-238 decay series. And here it started by the parents uranium-238. It will decay by ejection alpha particle to thorium-234. And the decay continue by ejection alpha particle and beta particle sometimes until reach a stable element lead 2.6. So the decay continue. And also we are interested in some chemical properties. For example, for uranium, it's dissolved in water. But for thorium, it's absorbed to surface of the grains. But actually in this study, we are interested in this part where 234, 238 exists. And later I will show you how uranium-238 and uranium-234 dBm per gram changing with time. And always there is a value for uranium activity. It's never start by 0. So I will speak here the activity changing in a closed system corals, and the initial value for uranium-238, it's about 2.5, and with increasing time, the activity of uranium-234 decreases with time, but the activity of uranium-238 is almost constant. This variation is because the decay constant of uranium-234 is much higher than the decay constant of uranium-238. And I will show how the activity ratio changing with time. And again, I will start I never start with value of 0 for activity ratio, and started by the activity ratio in seawater in a closed system like corals. So the activity ratio with increasing time in a closed system since no accumulation, the activity ratio decreases with distance until reach a value of 1 after 1 million years, which is called a secular equilibrium. And because there is an accumulation, there is no increasing in the activity ratio here. And I said there is a variation of uranium-234, 238 in the water bodies, and there many processes causing this enrichment. One of these processes is a process called recoil process, and I will explain it in details in the next slide. I back again to the uranium-238 decay series, and you see the parent uranium-238 decay to thorium-234 by ejection alpha particle and significant energy, and through this decay. The process is called the recoil process that I will define later. I will define it later. And the decay continue. So one mechanism that causing enrichment is the recoil process. But there is another mechanism, is the weathering, also responsible for enrichment of uranium-234 in water bodies. So due to the recoil process and during weathering process, the activity ratio is larger than 1. And for example, the activity ratio in the rivers is 1.5, but in seawater is 1.14. And here I said before that I will explain in details the definition of recoil process and its effect. So this figure shows the emission of alpha particle from uranium-238 and recoil effect. And I will start here to see that there is a grain of rock, such carbonate rock, and inside it there is a uranium-238. Uranium-238 will decay to thorium-234 by ejection of alpha particle, and alpha particle, it's helium. So helium will move about 20 micrometer in this direction. And because of there is some energy associated with this decay, there is a lattice damage. This damage, and because of momentum conservation, uranium-238 will reach the outer surface layer of the sea grain. This distance, the process where the recoil distance is called 34 nanometer. And uranium available in this distance will decay to thorium-234, but because thorium-234 is strongly absorbed to the surface layer, and because the half-life is short, it will decay to Ba by ejection beta particle, and because the half-life is very short, it's fast decay to uranium-234. If there water-rock interaction, uranium-234 will reach the water and may cause enrichment for uranium-234 in the water bodies. And beside the recoil, some uranium-238 will reach inside the grain itself and may reflect precipitation. Weathering process will occur here. So we have two processes, recoil process and weathering precipitation process. The recoil fraction is one mechanism control uranium-234, uranium-238 activity ratio. Besides to that, the weathering precipitation process also is another mechanism control activity ratio in the water bodies. And again here, I show you the cross-section, the hydrological cross-section. I show you that in the unweathered rock, the activity ratio is 1, but in open systems, such as waters, for example, surface water, the activity ratio changes from 1 to 2. But in percolation water, the activity changes from 1 to 3. And the activity ratios in the oceans is 1.14. And for example, in seawater, it's 1.14 for Mediterranean. So the values, all these values in open systems, such as waters, it's deviated from secular equilibrium, which is equal 1. And as the first case we want to study today, it's an example of carbonate rock. I will take a Tanyanim River as case example. So this is figure for Tanyanim River. And the main objectives is to describe the behavior of uranium isotopes along the flow path of groundwater, and we'll use mathematical model. And also we will quantify the effect of water-rock interaction process and the effect of alpha recoil on the activity of uranium-234 and its effect on the activity ratio in the water. And to achieve these goals, I will start to talk about one dimension, advection reaction decay steady state model. And as you see here, this is the groundwater flow. Inside, there is a groundwater contain dissolved uranium, and there is water-rock interaction occurs between the water and aquifer grains. So there's some input and output from the water and to the water. And for example, so there are input from the water and output from the water. The input of the water is supply the water by weathering dissolution process, supply the water with uranium by weathering dissolution process, and production. I said before there another process is the recoil process. So production of uranium-238 by alpha decay process. So we have here two inputs, weathering dissolution process and alpha recoil process. And we remove uranium from the groundwater by two processes. The first one, precipitation process, that we introduced a new term to the equation because there are two authors working on uranium transport, Trika and Maher. Both of them didn't introduce the effect of precipitation on the transport of uranium. But here we introduce a precipitation term, and another term for output, for uranium output, is the radioactive decay, particularly uranium-234. So all these parameters will introduce it to one-dimension advection reaction steady transport model. As I said, we introduce a new term, precipitation term. This is the equation for the model. The first model indicates for transport of uranium-238 in the groundwater, and the second equation is the transport of uranium-234. I explain each term. The first term represents the dispersive transport. The second term is the advective transport. This term represents the supply of uranium-234 to groundwater by a process of weathering, and this is the minus. This is remove uranium-238 from the groundwater by a precipitation process. Both equations the same parameters, but the main difference is the addition of uranium-234 to groundwater by alpha recoil fraction. So this is the main difference between the two equations. I simplify each term. Uranium-238W, uranium-238 in rock are the concentration of uranium-238 in the groundwaters and aquifer rocks, respectively, part per million. VA is the advective velocity of the groundwater. KD238, KD234 is the solution rate of uranium-238, uranium-234. And we here consider that the weathering rate for both elements are equals. Rho R, rho W, densities of aquifer rocks and the groundwater. N is the porosity, and Q is the void ratio. And the void ratio is defined by the rock density multiplied by 1 minus porosity over the porosity. And RF, this the term represents the precipitation and is defined the retardation factor and is defined by void ratio multiplied by the concentration of uranium-238 in water divided by the concentration of uranium-238 in the rock. DL is dispersion coefficient. So after that we solved the equation, and this is the solution of the equation. And we are interested here in the weathering rate, constant, and also the output will be recoil fraction. So from the solution of the middle, we have the weathering rate constant as output, and we have alpha recoil fraction as output. And the solution of the equation depends on fx and f prime x, and fx depends on decay lambda 238, age of the groundwater, and retardation factor. F prime depends on the same things, only the difference is decay constant of uranium-234. So again, the main output of the model we are interested in is weathering rate constant and the recoil fraction. Besides to uranium-234, 238, we will use another tracer, which is strontium-8786. The source of strontium-8786 is the weathering, And the main difference between them and uranium is there is no recoil fraction. So for strontium 8786, the only factor affects its concentrations or ratios, it's the weathering. So the main output of the model is for strontium is weathering rate constant. Here I show the model for the behavior of strontium 8786, and again I show you that the main output is weathering dissolution rate for strontium. And also we introduce here the partition coefficient, which represents the precipitation of strontium. As I said that actually we sampled different places. For example, we sampled in the north the Dan, also Golan Heights, Ain Bakura, and Tanyanim. Tanyanim is not part of Dead Sea watershed, but it is here as example for a carbonate rock. So we take it as reference for carbonate rock. And the second map represents the Tanyanim River watershed and the location of our samples in the Tanyanim River watershed. Here I show you the location of Tanyanim watershed. It's located in the north part of Yarkon aquifer, and it's important because it supplies the country by 25% of fresh water. This figure shows the geological formation of Tanyanim River, and I will speak about it in more details. For example, in Tanyanim River, we see that we have different formation, geological formation. For example, from the east there is Adulam formation, there is Mount Scobus formation, chalk, and some there are Bina formation, and some samples located, surface water samples located in alluvium, which represent soil. So therefore, Tanyanim River, there is different geological formation and lithology that samples located in. In this figure, I show you the Tanyanim River, surface water of the Tanyanim River, which is, I said, it's reference for carbonate rock, and with measured activity ratio of 1.130, and this is the measured value. And in Amikam Spring, the activity ratio is 1.114. And how we measure this activity value? When we go to the methodology, first of all, we sampled the water. For example, this picture in Bakura, and this water resulted from water-rock interaction. We took the samples and divided it into 3 portions. The first portion is for alkalinity, the second one for chemical analysis, and the third one for activity for uranium 234, 238, and strontium 87, 86 analysis. After we divided it, we did the chemical analysis. For example, for cations, we did its measurement in geological survey. For anions, we measured it also in geological survey. Alkalinity, we measured it in the Institute of Earth Science here at Hebrew University. And for high chloride concentration, also we measured it in the geological survey. After we finished with chemical analysis, we go to the isotopic analysis for uranium and strontium 87-86 ratios. What I will be focused here, that for concentration of uranium, we use it ICP mass spectroscopy, and for spectrometry, and for uranium 234 to 38 ratios, we use it NU plasma multi-collector, a geological survey. Again, I back to the study area, Tanyanim River, and I said there is a different geological formation, and according to the location of the sample within the geological formation, we divided the sample. For example, a group number 1, it's the samples located in Adulam formation. A group number 2, the samples located in Mount Scobus formation. A group number 3, the samples located in the soil, alluvium. And number 4, it's also the group located in alluvium, but the main difference that Timsah pond, it's high salinity water. And also we want to know what's the type of water we have in Tanyanim River. By analysis, we get that group number 1, number 2, and 3 is calcium, magnesium, bicarbonate water type. But in Timsah pond, it's belong to sodium, potassium, chlorine, sulfate water type. And this figure shows to distinguish between the two group of water, salinity or low salinity. The x-axis represents the magnesium and the y-axis the bicarbonate. So we see here there are different group of water in this area. And in this figure, we show in the first one, we show that for the calcium strontium, there is the slope of strontium over calcium, and the slope indicates the weathering precipitation process. And also for the second figure, the slope of bicarbonate to calcium also reflects the weathering precipitation process. And if we want to go to the relation between salinity and uranium concentration, again we see here two different groups, Timsah and Tanyanim water samples. And we're interested in this part of Tanyanim water, where there is a linear relation between total dissolved solid and uranium. And by using percent correlation, we can say that weathering plays an important role in surface water compared to the other water within the study area, as appears here from the percent correlation. So finally, from the chemical analysis, we can know that water in Tanyanim River is classified into two groups. One is classified by calcium, magnesium, bicarbonate types, and Timsah pond is classified by sodium, potassium, chlorine, sulfate water types. And also we can know that the weathering plays an important role in the surface water compared to other water of the other sample in the Tanyanim River. This figure shows east-west transect across the Tanyanim River. And later I will show the transect from east to the west. The black color represents the activity ratio. The red color represents uranium concentration. And as we see that the activity ratio is higher, the activity ratio is higher in Springs itself, for example in Ain Hafar, and in Amikan. But for surface water, as you see, the average activity ratio is almost constant, is 1.18. And this value represents the circular equilibrium. But as you see here, for example, in Ain Hafar, the activity ratio is high, but the concentration is low. So, and I want to say this for Timsah pond, there is no connection between it's separated because Timsah is another story because of its origin or salinity. Also, I wanted to show the change of uranium-234 and uranium-238, and show the slope of this represented, for example, in different the slope in different water samples. It's different from different group of samples. For example, for samples the group 1 it's 1.15, but the group 2 it's different, and the group number 3 is different, the slope. And in Timsah pond the activity ratio, the average activity ratio also is varies. So this shows the slope for each of activity ratio for each group. Again, I back to the equations. The equation, this is the solution of the equation, and again I say the main output for the model is the weathering rate, constant rate, and this is the recoil fraction. And this is transect from east to west for strontium. And also we see that in the strontium concentration in the black and strontium 87, 86 in the red. And we see that is the highest value, it's in the in springs itself. So I will use this data, introduce this data to one dimension advective transport model for strontium 87, 86, and the output is the weathering. And this figure represents we will show what's happening in Mecam as an example. For example, uranium-230, the activity ratio of uranium in the soil is 1.1, but the activity ratio in the rocks is equal 1. And if we look for the activity ratio in the water, it's 1.147. So it indicates this change indicates there is a water-rock interaction. And also, if we compare strontium 87, 86 in the water or the soil, 0.7087 and in the rock, 0.70785. But if we look to the water itself, 0.70825, it indicates that there is a water-rock interaction occurs. We will use this real data and introduce it to our model, as I will show you. So this is the output for the model. And actually what we did, we calculated for strontium, we calculated the weathering rate. And then we used it to see how activity ratio to change with distance. And I started first by taking the value 0.7087 in the soil. And for group 1, the weathering, the calculated weathering 4 multiplied 10 minus 6 per year. For the secondary group, 5 multiplied 10 minus 7 per year. And for surface water, 7 multiplied by 10 minus 7 per year. And for تمساح 1, 5 multiplied by 10 minus 7 per year. So this is the output for the model. And we calculated it according to the distance change. And later we will use this value to calculate what is the bulk weathering rate. So this is the groups and how the value changing with distance. And again, we use it, this is for strontium, we use it uranium transport model. And I said before we divided the group into 4 parts. And we use the model to calculate the weathering and alpha recoil refraction for each group. And the result of the group is for group number 1, recoil fraction 0.05, and the weathering is 2 multiplied 10 minus 6. And for group number 2, again, and group number 3, and the changing for group number 4. And the number for strontium, the weathering rate constant for strontium and the weathering rate constant that we get from uranium, it's close to each other. It's almost identical. So after I get the weathering rate constant, for example, I used it to evaluate the weathering of limestone in the carbonate terrains using uranium-234 and strontium 87, 86 data. So I show here that the average chemical weathering rate constant 6 multiplied by 10 minus 7 per year. And if I take a cube of a limestone of 1 kilogram and calculate the volume and using the porosity, by dividing mass over density, we calculated the weathering rate to be equal to 3 meters per million year. So in this study, the weathering rate of carbonate, it ranges from 3 to 9 meter per million year. But actually there is a REAP 2017. He calculated the long-term dilation rates vary from 6 to 20 meter per million year. So the average of our calculation locates in his data. Also in this study, for limestone, the alpha recoil, it's ranged from 0.04 to 0.16. But I said before, there's another one who worked on sandstone trica. In the trica, the alpha recoil, it's 0.1 to 0.3, and the weathering 3 multiplied by 10 minus 7. So the alpha recoil, it's larger, and the weathering rate constant in carbonate rock, it's 2 to 18 times higher than the sandstone. As I said that the first case was the carbonate rock, and Tellinin was the first one as a case. But for conclusion, alpha recoil changed from 0.06 to 0.16 in Timsah bond. And again, the weathering rate of carbonate rock ranged from 3 to 9 meter per million year. And compared to the REAP in 2017, it's 6 meter to 20 meter per year. But this is for a case study for carbonate. And next I will show you another case for basaltic rock that located in the Golan Heights. So the next case is Golan Heights. And the main objectives in the Golan Heights, the same as we will describe the behavior of uranium along the flow path in the flow path of the groundwater in basaltic aquifers, and also we will use a mathematical model, and also we will quantify the water-rock interaction and water-rock interaction, dissolution and precipitation, and the effect of alpha recoil on the activity ratios in water. So this shows the figure, this is a map of Golan Heights, and in the activity ratio, it's divided, it's range from 2.34 to about in the upper part of the Golan to 2.3 in the lower part of the Golan, as you see. This map shows the geological formation of the Golan Heights, and most of our samples located in the cover basalt, and we divided the samples into two groups based on analysis. The group located in the upper part near the Khula Valley, and the group in the lower part of the Golan Heights. Again, we did the chemical analysis for the water that belong to the Golan Heights, and the results show that water in the Golan belong to calcium magnesium bicarbonate. But if I introduce again the samples of Tellinin River, we see it's the same type of water. So to distinguish between the two types of water, we use equivalent sodium over chlorine ratio. And for basaltic water, always the equivalent sodium over chlorine ratio less than 1.05. That resulted from weathering dissolution of the basaltic rock. And in this figure, I show that also in x-axis sodium over potassium molar ratio, and the y-axis is uranium concentration. And it shows that there is a linear relation between sodium over chlorine and uranium. And from this figure, we can say that the group that locates in the lower part of Golan is considered low weathering plates compared with a group located in the higher part of the Golan. So the lower part, low weathering rate, and the samples located in the upper part is high weathering rate. And in second figure show the relation between total dissolved solid and uranium concentration, and is divided the samples into two groups again the samples located in the upper part and the samples located in the lower part. And it's shown here that the samples located in the lower part low weathering, dissolution, and precipitation rate according to the water-rock interaction. Also here we show that there is in the x-axis bicarbonate concentration and y-axis is uranium, and we see there is a linear correlation between bicarbonate and uranium and indicates that the samples located in lower part has a low weathering dissolution rate. And the second figure shows in the x-axis calcium, magnesium, potassium, and the y-axis represents the bicarbonate, and it's divided again the groups into two parts, and we can say that the samples located in the lower part of Golan has a low weathering dissolution rate compared to the samples located near the Hola Valley. And again, we use the advective transport model. There is no dispersion, the same equation. But here in this model for Golan, we consider there no dispersion. So it's advective transport model for uranium-238, and we use this model, and we get this is the solution of the model. And as said before, we're interested in the weathering rate of uranium-238 and the alpha recoil fraction. This is the main output of the model. And for strontium-8786, also the weathering is the main output for the model. So we have weathering and recoil from uranium and weathering from strontium. In this figure, I put samples on mixing diagram for strontium mixing diagram, and we can see that there are three components of mixing. Tanyanim river is, we put here Tanyanim river just for reference. It's not part of mixing, but just for reference for carbonate rock. So we have three main mixing points: Dan, Spring, Tanyanim river as reference, and Golan height samples. So three component mixing: basaltic water, Dan springs, and Tanyanim pipe as reference for carbonate water. We take the real value of measurement, and we take the value that where the Jordan River as a reference point, and according to that we calculate the weathering rate of strontium multiplied by 4.5 multiplied by 10 minus 8 per year, and introduce this value to the model, and we see here how the activity ratio changing with distance. And we did the same for uranium, and we introduced or put uranium data on uranium mixing diagram, and we see here the same thing, that Dan and Tanyanim river and basaltic reflect the three components points. And we use the real data again that we get from the mixing point, and we introduce that the output alpha recoil 0.047 and KD, and the second line, and we introduce it to our model, and we show how the activity ratio changes with distance, as you see. After we get the rate constant, the weathering rate constant, we can say that the average chemical weathering rate for basalt 2 multiplied by 10 minus 8 per year, and the same thing if we take 1 kilogram and 1 kilogram mass and divided it by density of basalt, we get the height of this cube, and we can be able to calculate the weathering rate as we get it equal 7 centimeters per million here for the basaltic rock. So the weathering rate for basaltic rock, the calculated is 7 centimeter per million year. Again, we go to a conclusion for Golan Heights. We can say that the average recoil fraction in Golan is 0.04, and this value depends on the aquifer geological, such as porosity and changing according to the porosity. And the calculated weathering rate for basaltic rock is about 7 centimeter per million year. And if we compare between carbonate rock in Tanyanim River and basaltic rock in Golan, we can say that the weathering rate of carbonate rocks 3 times higher than the weathering rate of basaltic rocks. So as take-home message, alpha recoil fraction in carbonate rock varies from 0.04 to 0.16. Also, the weathering rate constant in the carbonate rock varies from 300 to 900 centimeter per million year. Average alpha recoil fraction is different in basaltic rock and equals 0.04. And the weathering rate constant in basaltic rock is about 7 centimeter per million year. So the weathering rate constant in carbonate rock is 2 to 18 times higher than sandstone weathering rate. This is compared to the Etrika. And also the weathering rate constant in basaltic rock is from 15 to 60 times lower than the sandstone compared to Etrika 2003. I want to thank my supervisor, Professor Vital Bukman, Professor Mordechai Stein, and Professor Boaz Lazar, because I didn't able to finish this work course without them. And of course, thank you to my family. They are not here. And I want to thank the staffs in Geological Survey, Galit, Olga, Sabri, Anton, and Karen. And the staff in the Hebrew University, Ophir, Nurit, Adam, Levi, Daniel, Yael, Yussi, and Adi Ben Nom, and Adi Tolstein. And I will thank my friends, Omri, Rawi, Ilya, Yael, Bamella, Chen, and Reed. And of course, I will thank the secretaries at the Institute of Haifa University and the secretaries at the Institute of Earth Science at the Hebrew University. And thank you for your interest.
Questions?
So I have a question. An obvious one. You expand these results to the Dead Sea lakes, which have a typical delta 234 value. So have you expanded your model towards that, or are you thinking of doing that?
No, we didn't extend for Dead Sea itself. We just extended it for carbonate rock as example.
I was going to ask if, like you said, both the alpha recoil fraction and just the weathering rates in general are affected by physical characteristics of the rock, like porosity, So how do you separate the two? Or how do you separate the two effects?
We introduced to the model that what factors that we take a spherical rock. So introduce the model what factor that affect recoil and weathering, and by introducing the real data and the real porosity of the rock, we can emphasize how the porosity affects the recoil result. So every time I change porosity, I get another data, so it's depends on the geologic information.
So you can take the same model and apply it to different porosities based on what you input?
Yes, in different rock.
So I just want to comment that the recoil value you showed for carbonates was up to 0.14, right?
0.16.
0.16. So I think that's an undershoot, most likely, and I understand this was calculated from the solutions, but when you measure the rocks, silicate silicate minerals show recoil values which are as low as that and even, as high as that or even higher. And it's quite obvious that carbonates would have an even higher recoil value. So, I mean, great job, but just consider that the real signal in the rock, in the solid fraction, is higher than what you reported. Just a comment. That's it.
I have a very silly basic question. I hope it's not that I missed something, and sorry if I am. For the 87, 86 strontium, how do you get a rate out of it? Because they are both
We measure it.
stable.
No, the strontium 87 is depend on the source of the water, so it's varied from one source to another. So we measured it and compare what's causing its difference from one source to another. So it's not stable in all sources.
So what are your two sources? Like one is the rocks?
One the rocks and the other is the soil.
Uh-huh. So then you can only get the ratio between them, right?
Yes, but for example, in Sataf, strontium 87 in the water that we measured and in the soil didn't change. So we didn't able to calculate water rate because it didn't change by using the strontium model.
Okay. Then, so it's, I mean, the proportion between the two sources, it doesn't tell you if, for example, both sources are getting higher or lower.
Yes.
It's just the proportion between the two of them.
Yes.
Or have you, so to get a rate, have you assumed that one of them is constant and then you get the rate of the other one?
No, we consider the constant is the supply from the strontium. The supply from the strontium. Then across the distance, the strontium, as there is rock with water interaction, it changes with distance because there is an addition of strontium to the.
Yeah. So the supply is, for example, the soil. That's the initial
value
supply, and then whatever you get more carbonate, you assume that this is the carbonate rate. Okay. Yeah. Interesting. Thanks.
I also missed one thing that I didn't quite understand is what's the reason for the different values that you got in the upper, like in the exposed water and in the groundwater? Why would it be so different?
strontium 87, 86. It's depend on the initial composition of material.
So would it be the same because they're in the same ground, like a spring, for instance?
No, it's different because the soil, it's the origin of the soil, it varies. So what the origin of the soil came from, it's very strontium 87.
The soil, it's affected.
Yes.
More questions?
Okay, so we do the 60
Yeah,
seconds.
60 seconds.
Dalal, now you do the 60 seconds. So you explain to the people what they did not understand from your talk. And you have 60 seconds to say it. Go on.
Uranium activity ratio is important tracer for weathering constant rate. It's depend basically on the weathering of uranium and the precipitation and alpha recoil process. And in this talk, I focus on the carbonate rock and basaltic rock. So we introduced the data we measured in the recharge area and in the outcome of the springs, and introduced it to one-dimension advection transport model to get the weathering transport rate in the basalt and carbonate rock.
And what were the results?
The result that the weathering rate of carbonate rock is higher than the weathering rate of basaltic rock by 18 times.
Okay, thank you.